lungs and chest wall, and what influence this has on respiration. And so it has to do with the elasticity, as I said last time, and it's determined by the elasticity of the tissues, lungs and chest wall, and the surface tension in the alveoli. That thing about having to open and stretch the alveoli a bit. And as I pointed out to you, the stretchiness of your lungs and tissues varies with age and also with certain disease conditions. Emphysema, in which you break down the walls of the alveoli, means that you have a very high compliance, very elastic lungs, but doesn't really help you breathe because of the lack of surface area of the alveoli, the gas exchange, and fibrosis, in which there's replacement of lung tissue by scar tissue, which is no longer elastic. And so you have a hard time inflating the lungs, and this is an example of low compliance, where you need to do more work in order to expand the lungs. And this is all measurable and is usually expressed in what's called a compliance diagram. And this is what a typical compliance diagram would look like. So here is lung volume, and here is the pressure that you have to exert to inflate the lungs. Yes?
I have a question about emphysema.
Yeah.
You mentioned that it was easier for them to get air in.
Yes.
I was wondering, wouldn't it be more difficult for them to expel air?
It is. It is. When you see people with emphysema breathing heavily and deeply, they have a big barrel chest, and they actually have trouble, you're right, expelling air as well. And also the gas exchange is impaired. So multiple issues. Yeah, you're right.
I'm just confused on the notes if it was easy to get it in, but
It's easy to get it in,
difficult.
but difficult to get it out. Yeah, that's right. Very good. And so that will be reflected in the compliance diagrams that I'm just about to show you. So here is the lung volume, here is the pressure required to get air into the lungs. And so here is the curve for inspiration, and it's S-shaped here. And then for expiration, the curve is different. So expiration curve looks like this. And so this is called a compliance diagram. And this kind of situation where you have the curve go in one direction, different from the curve in the other direction, is called a hysteresis curve. And you might have come across this in physics and chemistry. It's just a physics and chemistry term for this kind of graph, a hysteresis curve. Now, why do you think the inspiration curve is different from the expiration curve? Any clues on that? Yeah.
One is active, the other one is passive.
Yeah.
So it's harder to get the inspiration started, but expiration is.
Yeah. So expiration is largely passive recoil, and so the force-volume relationship is different for expiration. Exactly. Now, on the succeeding pictures that I'm going to show you, the next one of these, I'm only going to show the inspiration curve, the active inspiration curve. So let's have a look at another one like this, only with the inspiration curve. So the green line in the middle is a typical compliance diagram here for a normal young active person here. And this is what happens to the compliance in these two conditions. First of all, decreased compliance, something like fibrosis, the curve is shifted to the right. And for increased compliance, something like emphysema, the curve is shifted to the left. So let's just have a look at that. For any given lung volume, let's take a line. It would be helpful to have a line drawn on this. Let's take a line across here parallel with the L. For any given lung volume, here is the normal pressure required to inflate to that volume. In fibrosis, look how much more pressure is required in order to inflate to the same volume. And by the same reasoning, for increased compliance, very little pressure is required to inflate to that volume. So that's the influence of compliance on the pressure-volume relationship. And as I say, these are measurable. And they're measurable in special labs, in hospitals. I don't know if I've been through this. Stop me if I've talked about this. Have I talked to you about this? Yeah, these pulmonary function labs. Did I talk to you? I'm teaching 2 classes at once, the same stuff. So forgive me if I've already talked about this, but in hospitals, the pulmonary department is huge. And they have pulmonary function labs there, and their job is to make lung measurements, functional measurements of lung activity, and it's done by a special group of therapists called respiratory therapists, and I know I've talked about those. I think, haven't I? Yeah. So the pulmonary function lab is where you would go if you have these lung issues, and they will measure compliance, they will measure the rate of airflow, which I'll talk about in a minute, and one of their main tools is a method called spirometry. Spirometry. I'm going to flip on a couple of pictures, because this picture should come next. And I really didn't do a good job of getting them in the right order. But this is what spirometry is about. They hook you up to tubes and ask you to breathe in and out. And as you breathe in and out, it goes through a variety of different equipment. This is an old-fashioned equipment. I think it's all done electronically these days. This used to be a system where you would move a tank up and down in a bath of water, and the amount that you moved, when you breathed out, you moved this up, and this was then translated into a trace on a drum. And it's still the same method, I think, but probably now all digital. And so what you can do then is measure various volumes in the lung for breathing in and breathing out. And there's a variety of volumes that are recognized and on traces like this. And so they'll hook you up to this thing, and they'll say breathe in, or just breathe normally, now breathe in maximally, etc., etc. And they come up with a whole series of volumes and capacities. So this is typically what they would measure. And so here you go. You're hooked up to the machine, and they say, right now, just breathe normally, and you'll breathe in and out and in and out like this. And this is your normal breathing volume, as you're doing right now. And that's called the tidal volume. The tidal volume is about half a litre. In fact, every time you breathe in and breathe out, you're breathing about 500 mils of air, about half a litre. I know what you're going to say. Do we have to know these figures? Well, no. Bottom line is no. But it's quite handy to remember 2 of them. And one of them is that the tidal volume, I'll show you the numbers in a moment. The tidal volume is about half a litre. Look, you see here, about 2.5 to 3 here. About 500 mils. And then they'll say, okay, breathe out as far as you can. And you go, more. 2 or 3 people there encouraging you, and breathe out as far as you can. And that takes the trace down here. And they'll say, okay, breathe normally, and you carry on breathing normally. And this volume is called the expiratory reserve volume. In other words, the amount that you can expire above what you would normally expire in breathing, the expiratory reserve volume. And one thing you'll notice immediately is that even when you expire as far as you can, you never empty the lungs completely. There's always air left in the lungs. And that's called the residual volume. The residual volume is useful. You can never get rid of all the air in your lungs, The residual volume is useful in case you inhale noxious gases, for example. You take a breath of noxious gas, goes into your lungs, you haven't got a lung full of this noxious gas because it mixes with what's already in there. So it ameliorates the effect of inhaling something nasty. I mean, that's a practical a result of having a residual volume. And then they will say, okay, now breathe normally, now breathe out, breathe in as far as you can. And so you breathe in as far as you can, hard as you can, and you get this picture on the trace. And this is called the inspiratory reserve volume, the amount that you can breathe in. So you can see, can't you, that the condition of your lungs will be reflected in these numbers, and also other numbers, which I'm going to show you a couple of slides down the line. And so they have these traces then, and so then they can crunch the numbers a bit, and they can combine the tidal volume with the inspiratory reserve volume, and you get this number from here to here, and that's called the inspiratory capacity, the amount that you can inspire. And they can do the same thing here with the expiratory reserve volume and the residual volume, and they call it the functional residual capacity. So they have all these numbers here. And then they can do this one here, the vital capacity. That's a useful one to know. That is from here to here, the maximal expiration to the maximal inspiration. How much can you get in and out of your lungs if you really try? The vital capacity and the residual volume, and then the total lung capacity is the combination of everything. The two numbers that it's helpful to remember are half a litre for the tidal volume and the total lung capacity, which is about 6 litres. About 6 litres your lungs can hold, 6 litres of air. It varies with your size, your age, your sex. Men tend to have a larger total lung capacity than women. And so all of these have normal values and normal ranges, and so they can compute the numbers and determine whether you're deficient in any one. So again, for a young adult male, tidal volume of a normal breath, about half a litre. The maximum volume that you can inspire is about 3 litres. Maximum volume that you can expire after a normal breath, about 1100. And the volume remaining after a maximal expiration is 1200 mils. So you still have more than a litre left in your lungs after you breathe down as far as you possibly can. And so these initial ones here are known as volumes. Inspiratory reserve volume, tidal volume, expiratory volume, residual volume. And when you combine them, they are known as capacities. So you can see anything which is more than one figure is known as a capacity. So here are the capacities. The inspiratory capacity, 3,500 mils. The functional residual capacity, 2,300. The vital capacity, about 4.5 litres. And the total lung capacity, about 5,800. How are you going to measure the residual volume? How are you going to measure the residual volume? You can't read it out. How do you know what it is? It's done, if you need to do it, which they usually don't bother, but if you need to do it, it's done by a method that physiologists love. It's done by a dilution method. So you give somebody a known amount of, say, of an inert gas like helium, a known amount of helium to breathe in. They breathe it in, and then they breathe out, and you measure the concentration of helium in the air that you breathe out. You know how much came in, you know how much came out, you know what the dilution is, therefore you know what the volume is that it was diluted in. So it's done by a dilution method, if you need to do it. So and it turns out to be, what was it? About 1,200 mils. There it is. Residual volume is measured by dilution of inspired helium. You can measure them all except for the residual volume. Is that okay? Pretty straightforward. I'm not going to ask you to remember all those numbers, but it's handy to remember a couple of them, as I said. Now, that really doesn't tell you the whole story, does it? Just measuring these volumes and capacities. Because remember something like asthma. With asthma, it's not really the amount you can breathe in, because if you breathe in slowly enough, you'll be able to do it. It's the rate at which you can breathe in that is the problem with asthma. If someone with asthma starts to run, then they have special difficulty, because when you start to run, you experience, what was it called, hypopnea, which is rapid breathing, and then you have to start breathing quickly. And that's their big issue, is not being able to breathe quickly because the diameter of the tubes is too low. You have asthma? No.
I have allergies.
You have allergies, yes. Same kind of thing. Asthma is an allergy, in fact. And so you can't breathe quickly enough. And so it's not all about the volumes and capacities, it's about the rate at which you can breathe, so that you can breathe. And so while you're hooked up to this machine, they will make another couple of measurements, and they will measure something called the respiratory minute volume. The normal amount of air inspired each minute. Well, this just comes from the volumes and capacities. So the normal amount of air that you inspire each minute, the tidal volume is about 500 mils, times about 12 breaths per minute. You breathe about 6 liters of air every minute. That they can measure from the tidal volume. Then they will measure something called the maximum voluntary ventilation. So you'll sit there hooked up to this machine, and they'll say, okay, I want you to breathe as hard and as quickly as you can for 1 minute. In fact, they do it for less than 1 minute and then multiply it out. Because if you did this for a minute, you'd probably collapse and be on the floor. So, and you know, they're there cheering you on. So you're sitting there and you're going, maximum in, maximum out, maximum in, maximum out, as quickly as you possibly can. That is the test of how efficient your airway is and the movement of air in and out. And it results in a number which is called the maximum voluntary ventilation, the largest amount of air that can be moved in and out of the lungs in 1 minute. And it's a measure of muscle power, and it's a measure of airway resistance, which is the diameter of the airways, essentially the diameter of the airways. If you have asthma, if you have allergies, you won't do very well on this test. And the maximum amount of air that you can move in about a minute comes to about 150 liters. So all of these numbers are used by pulmonary doctors, pulmonary function lab, pulmonary therapists, and there are a lot of them in hospitals dealing with these issues. Any questions? Anyone got any personal experiences they'd like to share? No? Okay. What do your allergies do to you when you have them?
Like very bad ones. Basically, I can't really breathe and I can't pass out.
You can't breathe and you pass out?
Pretty much, yeah.
Yeah?
Yeah.
Do you have any medication that you use? Yeah, right. Puffer?
I used to be on one once. They used to think I had active straight asthma, but they didn't realize it was my allergies.
Right.
Like just pretty, yeah, so.
Right.
It's getting there though. But
Yeah.
I probably have
Right. There you go. Quite debilitating. Any other comments, issues? All right. Look, we've looked at this picture before last week. Do you remember it? Someone brought up an issue. Was it you, wasn't it? Yeah. Yeah. So this picture comes up again because of what we're going to talk about next, which is the alveolar ventilation. But let me just go back to that issue that we talked about last week. You remember what it was? The fact that on this particular picture they show you alveolar pores, not just going into the alveoli from the alveolar ducts, but between the alveoli here. And someone up the back there noticed this and pointed it out, and she's absolutely right. And I've been thinking about this, and there are these pores between the alveoli, and I realized that the reason that I at least disregarded them and didn't even bother to mention them are because of these damn cartoons that we use all the time. This is a cartoon, right? This is an artist's impression of what the lung looks like. And it doesn't actually look anything like this. I mean, it's like all of the pictures that he show in the nice textbooks. They're all simplified and they're all dumbed down so that you can get the concept, which I suppose is valuable, but it doesn't actually tell you what these things look like. So if you were doing research in lung physiology, and you were looking at lungs all the time, wouldn't actually look anything like this at all. Let me go back to, I've got a few minutes to talk about this, I think it's quite useful. Let me go back to the picture that I showed last week on this. Here it is. Here was the original that we looked at last week, and then the next picture, look at the next picture, is like this. Which I'm sure at the time you thought, well, hold on a minute, that doesn't look anything like this. And of course it doesn't look anything like this. This is a somewhat more reasonable representation of what a slice, or a section as it's called, through lung tissue would actually look like. So if you're in the lab, you're a grad student or whatever it is doing research on lungs, and your supervisor tells you to cut sections of this rat lung, you wouldn't see anything like this. You would see something more like this, and it's closer to what the lung actually looks like. And you know, they're not uniformly shaped bunches of grapes and bubbles. You know, one gets sucked into these simplifications, and this is a response to that. If you look at this picture here, which is actually more representative of what a slice of lung. I've seen slices of lungs, and they look much more like this. This is not a bad representation here. And here's another one, and another one, and here's part of another one, and part of another one, and part of another one, part of another one. Look. You see that? It's in this picture too. So the alveoli are really almost a network of small air spaces. Not simply these things on the end. So it's good that you pointed that out, because it pulls you up short and you get seduced and sucked in by these simplified diagrams, which are really not what the tissue looks like. Anyway, so that's my explanation of that. And I suppose the takeaway message is that when you use your textbook and look at pictures like this, you know, don't get carried away, because it actually doesn't look anything like this. This is a cartoon which is done by an artist to represent what is there, the concept. They're concept pictures. They're not real pictures, and it leads you to make mistakes. Okay, that I think is the answer to the issue that we had last time with the ducts coming in between the alveoli. Any comments on that? You know, it's sort of a conceptual issue of these kinds of beautiful pictures that the textbook companies suck you in with. I'm not saying they're not useful, I'm just saying that they're not real. Yeah? Any comments? And this may apply to other stuff that you do too. So I guess what I'm saying here is you've got to develop a sense of critical thinking when you read stuff. When you know, at your level, when you read your textbook, think critically about what it is you're reading. And as you get further and further, fourth year, third year, fourth year classes, you know, professors would expect you to think critically and not accept everything that you see in diagrams or in writing as necessarily true. End of sermon. Okay, so look, we're on to a new topic here, alveolar ventilation, getting air in and out of the alveoli. And it's a continuation on of compliance and all of these things. You remember the issue of the conducting system versus the respiratory parts. So the respiratory parts down here in these things called respiratory bronchioles. Can you see in this cartoon? Not going to really look like this cartoon. There are gas exchange bubbles here on the respiratory bronchioles, but most of them are in the alveoli. And so alveolar ventilation refers to the volume of air reaching the alveoli per minute. The alveolar ventilation is accomplished by movement of the alveolar ducts. Remember, there's a certain amount of movement. There's some muscle in there which enables them to, not very much, but to change in size. The alveoli themselves don't change much in size. There's not a huge amount of expansion. And of course, they don't collapse. We talked about that. Now, here's an issue. Only the gas in the alveoli counts, in quotes. In other words, only the gas in the alveoli is involved in gas exchange. And the gas in the rest of the tract, which is called dead space, doesn't participate in gas exchange. Now, maybe I said this before. I don't remember. I get confused between two classes. But if you were actually designing a respiratory system, you wouldn't design it the way ours is. Because what we have is a system where you draw air in through one tube. The only bit that's really involved in gas exchange is right down the bottom here. And all the rest from here is dead space, which doesn't actually do anything. So you breathe it in, and then you have all the work of breathing it out, and then you breathe it in again, and you're not exchanging most of the gas. Most of the gas, a lot of the gas is just going up and down here in the dead space. If you were designing, if you were an engineer and someone said design a system for respiration, what you'd probably do is you'd design one tube for gas to come in, circulate it through the lungs, and then another tube for the gas to come out, so that all the gas that you inspire gets circulated through the gas exchange membranes and then out again. You extract all of the oxygen from the air that you breathe in. This little note here reminds me to say that if you do comparative physiology, we don't do comparative physiology here, but if you do physiology over in the biology department, and you do comparative physiology among different animals, then you might find out that birds have a much better system than we do. In birds, they also have a single tube in, and then they circulate the air through the lungs and then breathe it out. So they have a mini circulation system in the lungs before they breathe the air out. And so much more of the air is used in gas exchange than in our case. So birds have got it a bit better. Not perfect, but they've still got it better than we have. So this stuff, this air that doesn't play any part in gas exchange is called dead space. And so the alveolar air volume is the tidal volume, remember, about 500 mils, minus the dead space volume, which is about 150 mils. And so every time you take a breath, you're taking 500 mils in, but only about 350 mils of that actually gets to the gas exchange membranes. So the alveolar air volume is about 350 mils. So let me just talk about dead space for a minute, because it's It's a huge part of what you inspire every breath. The anatomical dead space is the trachea, the bronchi, and the upper bronchioles, most of the respiratory tract. And then, if you're young, healthy, that's it. But if you have other physiological issues, then the so-called physiological dead space includes, it's the anatomical dead space, plus the inactive alveoli. So someone without emphysema, who has a lot of inactive alveoli, is going to have a huge dead space. Going to have the anatomical dead space plus the volume of all the alveoli that are shot and don't work properly. So the physiological dead space is significant in some diseases. So if you take, what did I say the dead space was? About 150 mils times 12 breaths per minute, roughly what you would do at rest. 1,800 mils per minute of dead space ventilation doesn't participate in respiration at all. Absolutely inefficient and useless. I found this picture in a book which illustrates that. I'm not sure how effectively. Got a couple of pictures here that I'm not sure how effective they are, but it gives you a feeling for what I'm talking about here. So here is the alveolus. So this is the respiratory part of the lungs. This is the beginning of the conducting zone that doesn't play any part. Here is a breath care coming in. So this is old air here that's been breathed. This is fresh air which hasn't been breathed. You breathe in and you draw in some new fresh air, but not all of it. You actually, because you didn't expire everything, you draw in some old air as well, and then that all gets used up, and you get fresh air here, which isn't participating in gas exchange, and this has done, and then you breathe out, and you get to this situation. So you can see you're breathing in and out old air, and not a complete alveolus full of new air even every time you breathe. So not efficient even at the best of times. So that's the concept of dead space. Any issues, questions about dead space? So here's alveolar ventilation then. The rate of alveolar ventilation, 12 breaths per minute, times 500, which is the tidal volume, minus the dead space, about 4,200 mils per minute. I'm not going to test you on these numbers. You don't need to know these specific numbers. But, I mean, it won't hurt you, wouldn't kill you if you did know them, but I'm not going to include them in an exam, so don't worry about that. So that's the concept of alveolar ventilation with dead space. So the alveolar ventilation determines the concentration of oxygen and carbon dioxide in the alveoli. Now we're beginning to get to the nitty-gritty of respiration, the gas exchange. The alveolar ventilation determines the concentration of oxygen and carbon dioxide in the lungs. And here's the thing. The alveolar ventilation may not be uniform across the lung. It depends on regional variations in lung expansibility. Here's something I haven't talked about. One lung here and one lung on the other side. And we're talking about air going in and air going out. But lungs are big. Have you seen lungs? You can, did anyone see the, what was the name of that human exhibition on at the museum a few years ago? Did you see it? What's it called? Yeah, what's it called? Bodyworks, yeah. Did anyone go to Bodyworks? Absolutely fascinating, wasn't it? And they show you lungs there, and they show you lungs that have been involved in smoking. And when lungs are expanded, they're big. I mean, they're from about here to here. But they're not the same all the way through, in fact. And the pulmonary people really get off on this. Different regions of lung efficiency. And so the ventilation of the alveoli is not necessarily the same at the top as it is at the bottom. And there are variations in lung efficiency across the lung. And it has to do with this issue. called ventilation-perfusion ratio. And the pulmonary people love this for some reason. I guess I can understand why. Because it really gets down to the issue of efficiency of gas exchange, which is what respiration is all about. Put down your pens for a moment. I'm going to make a fool of myself in the front. So just put your pens down and watch me make a fool of myself. Ventilation-perfusion ratio. So ventilation is the air going in and the air going out. We just talked about. No. Like that. Like that. Air going in, air going out. Perfusion, the word perfusion, means the flow of fluid, or gas, in this case fluid, through a system. And in this case it refers to the flow of blood through the lungs. So you've got the blood flowing through the lungs here, picking up oxygen and releasing carbon dioxide. So here you've got perfusion, and here you've got ventilation. This is hard. Okay? You've got ventilation on this hand, and you've got perfusion on this hand. And so the new air comes in, the new blood comes round, and bam, gas exchange. Oxygen one direction, carbon dioxide in the other direction. And then they carry on. And when they come together, bam, thus gas exchange. In order for there to be efficient gas exchange, you've got to optimize the rate of ventilation with the rate of circulation or perfusion. If you have too slow a ventilation and a rapid circulation, then the blood is going to be going around, and every time it comes around, it's going to still find old air there, so it's not going to exchange properly. The opposite way around, you've got a nice rapid ventilation, but a very slow circulation. Then you've got new air coming in, but no blood to pick it up. Do you understand what I'm trying to say here? You've got to optimize the rate of ventilation with the rate of blood perfusion. It's called the ventilation-perfusion ratio. And that has to be optimal for efficient gas exchange, so that the new air coming in can exchange with the blood coming round, take up the oxygen, release the carbon dioxide, and it has to happen very quickly, because the blood is circulating all the time, you're breathing in and out all the time, there's only a certain window in which to do the exchange. And that's called the ventilation-perfusion ratio. And ventilation, the delivery of air, perfusion, the delivery of blood. And neither of these are uniform throughout the lung. I'm not going to go into the details of this, but I know the pulmonary guys love it. And optimum gas exchange requires an optimum ventilation-perfusion ratio. And in various diseases, there's an abnormal ventilation-perfusion ratio limiting the efficiency of respiration. That's why the pulmonary guys like it, because it's an indicator of various pulmonary problems. Here's another picture which I thought seemed like a good idea at the time, and really it's useless. This is a lung, and all it does is it's one of these bloody cartoons that suck you in, and you think, oh, this is great, and then you look at it and you think it's absolutely useless. It's a cartoon indicating that the alveoli are different in different regions of the lung. So up here, they're shown as sort of large spaces. Down here, they're shown as small spaces. Up here is a lighter color. Down here is a darker. I don't know what the hell that means. The takeaway message from a picture like this is that the lung isn't the same everywhere. That's all you can say about this. And so there are normal differences in the alveoli in different regions of the lung, and this results in normal differences in the ventilation-perfusion ratio in different parts of the lung. This actually came with the picture. Let's have a look, see if we can make any sense out of it. The apex is up here. The intrapleural pressure is more negative. We know what intrapleural pressure is. Gives greater transmural pressure. Therefore, larger alveoli. Because there's a larger transmural across the wall pressure, the alveoli are more expanded at the top than they are at the bottom. So they're alveoli. There's a lower intravascular pressure up here, as well. So the about lower pressure, there's less blood flow, so there's less ventilation and perfusion. So the ventilation perfusion is lower up here than it is down here. And they can measure this and look at different regions of the lung and see how, not simply how you're doing, but how different regions of the lung are working too. You take a course in pulmonary physiology later on, they'll go into this in much more detail. Well, you know what? We're on to the nitty-gritty of respiration finally, after 3 classes, halfway through. And the next section starts with gas exchange, which is actually how the gases are exchanged in between the alveolar space here, across the respiratory membrane, into the blood, and we're going to talk about that, and I'm going to leave that until next time. So we'll start with gas exchange.